This is going to be an overview of the WPILib Command Based structure for 2025 for FRC robots. We are going to be looking at the de facto standards, which is the current best practices for programming. There are no firm correct ways to do things, but this is what is considered standard and optimal to use. We will start with the structure of the program. The structure will apply to Java and C++ programs. This is less relevant for RobotPi and not relevant for LabVIEW. Like any Java program, we will start with a main class. This is going to be preset in all projects. We do not touch this class. There's no reason to ever touch it. We do not touch it. What we will be touching, potentially, is the robot class. This is going to be having an instance inside of the main class by default, and this one we can and will likely edit. So the important thing to understand about how FRC robots work is that they all operate on a 50 Hz, which is a 20 millisecond system loop. That means everything must happen within this loop, and it also means that we cannot easily do simple procedural actions because it is all looped and we cannot control the loop in any way. It is set and cannot be changed. So there are the two main methods of programming. There is the timed robot method, where timers are used to set positions, and state machines can be made custom to control different conditions. The other method is command-based, which essentially has built-in state machine functionality within the libraries, the WPI library, and can be used to create subsystems and commands. We're going to be looking at command-based. Next class involved is robot container. In command-based programming, this is going to be where a lot of things happen. Robot will have an instance of robot container inside of it, and this robot container is going to contain subsystems and the controls of when those subsystems run commands. The robot container will also contain each instance of a subsystem that we will use. Now we have the subsystems and the commands, so it is good to understand what these are and their relationship with each other. The subsystem is a group of devices analogous to their physical counterparts, which we will be controlling, and the actions the subsystem takes is in the form of commands. Now, commands are going to be objects that encompass specifically the action done by the subsystem. A good indicator is that a subsystem will usually produce a command and may return it as a function, or commands can be created in other ways. But important to note is that a command will always, in some way or another, require a subsystem. This is done as somewhat of a safety measure to ensure that the subsystem does not attempt to run two different commands at the same time and perform conflicting actions. Commands can be made that require one system, multiple subsystems. There are multiple ways to do it, but the important part is that commands will require the subsystem that they use, and when they require a subsystem and you schedule a command and that subsystem is already in use by another command, depending on the settings, but by default, that command that is currently running will be cancelled so that the new command can run. Now, before we look at the code specifically, it is good to have a overall understanding of the two types of devices we will be controlling from. This is the RoboReel, the main brain of the robot. Most computation is done here, and this is the device we are explicitly controlling by default. All WPILib imports and classes will run directly on the chip of this RoboRio. If we follow the CAN cable, which is the primary connection bus for modern devices, we will reach the motor controllers. So here we have some examples of what are the two most common ones, the Rev Robotics Spark Max and CTRE Talent FX. Both of these are going to have their own imports in the code, and their specific classes will have special control functionality for PIDs and other things that will run directly on the chips of these motor controllers. This offloads some processing from the very weak RoboRio CPU and is, at least theoretically, marginally faster. Now, a good thing to understand before we look at the code itself is going to be the file system. We're going to start with the main project folder. There will always be one of these. It will contain several other folders inside it. The main one we're interested in is source, that's SRC. Inside it, it's going to be main of these two folders, deploy and Java. Deploy will be for extra information and files if you have certain libraries for things. The main code is going to be under Java, and then this is where the main file system will be contained. Now, this is going to be a typical structure for a command-based project. We are going to have, as said before, main, which we do not touch, but as you can see, we have an instance of the robot being started in here. Then we have the robot.java. This is going to be the robot file. This is required for all projects. Now, this does say timed robot. Do not be confused by that. We are still looking at a command-based project. All command-based projects do run under the timed robot format. That is how the robot class works fundamentally. And you can mix things. For example, if you wanted to use a timed autonomous, you could do that. Now we get to what could be the more interesting component. This is the robot container. As we look at the robot container, you'll see that there are the instances of a controller and a subsystem here. Of course, this is very simple. We only have one controller and one subsystem, but it shows the relevant details. Whenever we declare devices in a class, we are going to initialize them with new in the constructor. This is also where we are going to bind the buttons to certain commands to get the subsystems to do things. That will be done in the configure button bindings method, which is then called in the constructor as well. The final thing that is in the robot container is the autonomous command. We can put an autonomous command in here, or multiple if we would allow for the choosing of an autonomous from a list of multiple. That is a very common thing. Now there is an additional folder over in the file system. This is typically the subsystems folder, and we will look at a subsystem now. Now, as we said before, the subsystem is going to be a grouping of real devices that are going to be working together. Of course, the important thing to note is that when we schedule commands, that is going to cancel the actions of other commands. So if these things need to be doing different things at the same time, maybe they should be in different subsystems. That is one way to think about it. It is more a way of organizing and controlling things. So looking at this subsystem, we have declared several different devices in here as their classes, and then we'll go and initialize them in the constructor. What we have here is a Rev Robotics Spark Max brushless motor controller. This is what you're going to have powering Neo 1.0 and 1.1, Neo 550, Neo Vortex, and brushed motors. To go along with it, we have its PID controller. We will need that to control it. This Talon FX is a CTRA Talon FX that's going to power the Falcon 500, Kraken X60, and Kraken X44. We have its position, voltage settings that we will need to control it. We have a sensor here. This is a digital input, so this could be any sort of sensor that sends a digital signal to the robo-reel. In this case, we'll call it limit. We'll assume it's some sort of limit switch. Now you could also have things like photovoltaic sensors, anything that sends a digital signal through the DIO ports of the robo-reel. And finally here for a bit of pneumatics, we have a solenoid. In the constructor, we are going to be initializing these devices, so let's start with that Spark Max. Now, something to consider is that for CAN devices on the CAN bus, they will each need a unique device ID. And a consideration is that if you are going to have multiple instances of this subsystem, if you have multiple of this type of part or system on the robot, it is going to be necessary to pass that CAN ID in as a parameter, which is what we are doing in this case. So this integer value is passed into the CAN ID slot of the Spark Max constructor. The other thing we're doing is setting the motor type as brushless, as this motor controller can power both brushed and brushless motors, so we need to specify. Down here, we are going to be setting the max config, which is going to be the configuration settings for the Spark Max. This is going to be the closed loop settings for operations under the PID controller. We will set the P, I, and D values with output, input, and the idle mode. This is going to be what the motor does when it is not doing anything. We're setting this to brake, which will hold its position somewhat. It's not strong, but this is how we are going to set it. And then we are going to order it to configure these parameters. Then we are going to specify what the PID controller is from it by calling get closed loop controller. Next, we're going to look at the Talon FX. If the subsystem is going to have one instance, we can pass the CAN ID value directly. We have no real reason to pass it as a parameter, but there's no reason that you can't. So we are going to be going about with the configuration of this. We will be creating a new configuration, and this is set slightly differently, but basically doing the same things, P, ID, and the, in this case, neutral mode. This one will also be set to brake, and applying the configuration. Now, this is going to be the initialization of our limit switch, which is the digital input. This one is going to take its DIO number, that's the number of the DIO port on the robo-reel. And then the solenoid is going to be passed with its pneumatics module type, which in this case we're going to assume is a rev pneumatics hub, and its solenoid port number, which is the second argument. Now, what we have done here is the default command. And subsystems can have a default command that will always run when another command is not scheduled. If you schedule another command, that will, of course, interrupt this one and take over. But once that command ends, for whatever reason, if another command is not scheduled in its place, this default command will be scheduled and will run automatically. So in this case, we are setting the default command of subsystem to foo. Now, something that we might do in here is if we have a complicated set of actions that needs to be done, we won't create a command directly. It might be easier to make a regular void function. But in order to ensure that this is used correctly, we will make sure that all functions that could be controlling things and aren't returning commands are set to private. For example, this one is going to be sending the motors to a certain position. This is just demonstrating the way we would do that for each one. So for a rev device, we are going to call not the motor controller itself, but its PID controller, and set reference to a set point, and set the control type, in this case position. We're doing a position set point. For a CTRE motor controller, at least Phoenix 6, so this is going to be only Talon FX and Talon FXS. We will use the position voltage that we declared above, and with position, we're going to set the position. These should be doing the same thing. This is just the different types from the two different vendors. Another thing we might have is a function to check the state of the limit switch. Now, an important thing to note is that by default, the digital inputs return true. And so a limit switch, which is not active when it's not pressed, the circuit does not complete, is going to return true when it's not pressed. So a lot of times we are probably going to want to invert that value in order to see what is actually happening. Now, when it comes to actually creating a command so that this subsystem can complete actions properly, when inside a subsystem, which is the preferred way to do things, we can do run to have a command that is going to run continuously and not stop until it is cancelled. In this command, we are going to put the function or functions that we want to complete. This motors to position as we had up here. What is important to note is that when we are creating commands, the functions are always going to be passed as lambdas. And so that is going to be the open paren, close paren, hyphen, greater than before the function. That is necessary. Down here, we have an example of another command, but this one is only going to run once when it is called, because it is a version of run once. Again, we have a lambda. We always need to have that. And this is an example of a command composition, because to start, we are going to call the solenoid to set, and that's going to deploy it. And then we are going to use the and then decorator to begin creating a composition. This will indicate an action that happens sequentially. And we are going to initiate a wait command to get it to wait for 1 second. We'll use another and then to add to this composition. So this is an additional sequential action with another run once, lambda to solenoid retracting. Now, there are other ways that you can combine commands, but as of the moment, this is the preferred method because it is simple and easily readable. An important thing to understand is that we are inside the subsystem at the moment, so all of the commands created here, by default, require this subsystem. That requirement is ensuring that we cannot schedule another command using this subsystem at the same time as one of these. If you are declaring a command outside of the subsystem, they will usually have a parameter that needs to be filled with the subsystems that they will require. What you may have noticed up here is that there are a lot of constants that are in a subsystem constants class. Now, this is a very common way to do things. Some people will put relevant constants in the subsystem file itself, but most commonly we'll have a separate constants file that contains those constants. So as we have here, we have the constants class, and then within it we will have additional classes relevant to each subsystem, and also in this case the driver controls. That is also very common. These are not real values, these are just placeholders, but this means the constants can be easily accessible if needed from anywhere. That should be an overview of most of the classes themselves. One final thing to look at is some of these imports up here. There are many, and some come from the manufacturers. These come from vendor libraries that must be installed. These can be done manually, but new for this year, we can see available vendor libraries from the WPILib Vendor Dependencies tab on the left. This is an overview of most basic concepts of the command-based system. Of course, every implementation will be different, but this is a somewhat standard concept.